Hello everyone. In today's video, we'll be going over mole-to-mole problems and how to use the coefficients of a balanced chemical reaction to calculate the moles of one substance from the moles of another. So let's get started. Mole-to-mole problems. All right, so this is the foundation of stoichiometry. So I'll first go over the general idea, and then we'll go through several examples from the quizzes earlier this week. Okay, so it takes a little bit of exposure to several examples over and over again before you start to see the pattern in these problems, because they're all actually very similar. All right, so in general, this is a problem where you have a balanced chemical reaction. So, for example, you could split water into hydrogen and oxygen. And maybe the question is, how many moles of water are needed to produce some number, right? Some number that's given to you. Maybe it's 17 moles of O2. Okay? Well, to solve this problem, we're taking 17 moles of O2, and we need to find a way to convert that into moles of water. So it's a type of unit conversion, changing the units from moles of O2 to moles of water. Now, like any other unit conversion, right? Any unit conversion, you can do that conversion using a conversion factor. In this case, the conversion factor in a mole-to-mole problem, so the conversion factor in a mole-to-mole problem is a ratio of the coefficients. Let me explain what I mean by that. All right. So if I look at the balanced chemical equation, it's telling me, I'll write it up here. The coefficients in that equation are telling me that 2 moles of water make 2 moles of H2 plus 1 mole of O2. So the relationship between water and oxygen is basically 2 moles of water makes 1 mole of O2. Okay? So this is kind of like a recipe, right? 2 moles of water makes 2 moles of H2 plus 1 mole of O2, which means that if we wanted to make 1 mole of O2, we would need 2 moles of water. But in our question, we don't want to make 1 mole. We want to make 17 moles. So we're going to have to scale that recipe up, right? We want to make 17 oxygens, right? We want to make 17 of them. We're going to need to, and we know that we get 1 oxygen from 2, right? So we're going to need to scale this up, right? So one way to do this is to take 17 and divide by the coefficient of O2. So in this case, that's just 17. And then, like a recipe, I'm going to scale the recipe up by multiplying the entire recipe by 17. that means that 17 oxygens are going to be made alongside 34 H2s and from 34 waters, right? So the answer would be 34 moles of water are needed to make 17 moles of O2. Now, that's the answer, and that logic should make sense, right? If you need 2 moles of water to make 1 mole of O2, if you're going to make 17 moles, you need 34 moles of water, right? Because you need to multiply your whole recipe by 17 to make sure you're getting the 17 moles of oxygen. Now, to see the conversion factor for that, 17 moles of O2 is what we're starting with. The conversion factor is going to be a ratio of what we want. We want to find the amount of water to what we're starting with, right? And for a mole to mole problem, that conversion factor are the coefficients, right? So if I look at the equation one more time, my coefficient for water is 2. My coefficient for oxygen is 1, right? So I'm going to use those coefficients in my conversion factor. Actually, let me keep that red. 1 oxygen for every 2 waters. And so I end up multiplying my moles of oxygen by 2 over 1. And that gives me 34 moles of water. So my general approach to these problems is to find a ratio of the coefficients that are going to change the units, right? So if I have moles of a substance and I want to find moles of a different substance, I can always solve this problem by multiplying by the ratio of the coefficients. So the coefficient of what I'm converting to on the top and the coefficient for what I'm converting from on the bottom. Right, this is kind of it, right? This is kind of it. All right, now let's take a look at some of those example problems from the quizzes, all right? The first one, we've got, let's see, calcium chloride plus sodium. Makes sodium chloride plus calcium. So this is a single replacement reaction. Now to balance this equation, I need a 2 here and a 2 there. Okay, and the question was, how many moles of NaCl can be produced from 8 moles of calcium chloride, right? So we're starting off with 8 moles of CaCl2, and we want to know how many moles of NaCl that's going to make. Okay. So I can do this a couple different ways. I can treat this as a recipe, right? And then scale it up, right? Or I can set up a conversion factor. So let's do it both ways. Let's do it both ways. First, the recipe. Okay, So the recipe is as follows. 1 calcium chloride, right? 1 calcium chloride plus 2 sodiums makes 2 sodium chlorides plus 1 calcium. So all I've done here is I've rewritten the equation, and where there is no coefficient, I've put in a coefficient of 1, right? Because that's what's implied here. Okay, so we know that one calcium chloride is enough to make 2 NaCl's. But we're not starting off with 1. We're starting off with 8 moles of calcium chloride. So we're going to have to multiply, let's see. We're going to have to multiply this recipe by something, right, that gives us 8 moles of calcium chloride. And then we'll see what we get for NaCl. Well, 8, we're going to take 8 moles, what we're starting with, and divide by that coefficient, 1. That's just 8, which means then that I need to take my entire recipe and scale it up by a factor of 8, right? So that means that, all right, this becomes 8. This is 16, 8, right? So that means that if I had 8 CaCl2, I would need 16 sodiums, and I would make 16 NaCl's and 8 calciums, right? This is the same, this recipe has the same exact proportions between all the reactants and products. We've just scaled it up for 8 moles of calcium chloride, which means then that we're going to make 16 moles of NaCl. So that's the recipe way. Let's look at the conversion factor. Let's look at that conversion factor. So here's the equation. Right? And we've got 8 moles of calcium chloride. And we're trying to find moles of NaCl. So we're going to take 8 moles of ClCl2 and multiply by the ratio of these coefficients, right? So we're converting to NaCl, so we'll put the coefficient for NaCl on the top and the coefficient for what we're starting with, CaCl2, on the bottom. And so we end up doing 8 times 2 over 1, and that's 16 moles of NaCl. All right, so we did this problem 2 different ways, and in both cases we get 16 moles of sodium chloride. Okay. All right, let's look at the next one. All right, the next one, we've got the same equation. So CaCl2 plus 2 sodiums makes 2 NaCl plus calcium. Now the question is, how many moles of NaCl can be produced from 5 moles of sodium? Okay, so let's solve this problem with a conversion factor. We've got 5 moles of Na, and we want to know how many moles of NaCl that's going to get us, right? That's going to be produced from this reaction. So 5 moles Na, going to multiply by conversion factor. And remember, the two things of a conversion factor that's important. The top has to equal the bottom. They have to be equivalent. And the units have to cancel so you end up with the units that you want, right? And so we want moles of NaCl. So what this conversion factor is a ratio of moles of Na to moles of NaCl, right? It's a ratio between those two moles that, it's like the exchange rate. It's how those two quantities relate to each other, right? And so I'm going to put moles of Na on the bottom and moles of NaCl on the top. And that way moles of Na are going to cancel. That unit is going to go away. And in here, I'm going to put the coefficients. So I'm going to put this coefficient for sodium. And I'm going to put this coefficient for sodium chloride. So I'm going to get 5 times 2 over 2. So that's just 5 moles sodium chloride, which should make sense because we know that 2 moles of sodium make 2 moles of NaCl. So that's an equal number, right? So if I scale this up to 5, I'm going to still have an equal number of sodium chlorides as I have sodiums. Okay. Next one. All right, now we're going to do a decomposition of aluminum hydroxide. So let's see, what does that look like? Aluminum hydroxide is this. It will decompose into aluminum oxide plus water. And we've got to balance this equation. There's 2 aluminums on the right. So let's put a 2 here. And that gives me 6 hydrogens. So let's put a 3 here. There's 6 O's and 6 O's. So we're good. And the question is, how many moles of water can be produced from 6 moles of aluminum hydroxide? So how many moles of water can be produced from 6 moles of AlOH3? Okay, so let's solve this problem using a conversion factor. We can also think about it logically. 2 moles of AlOH3 make 3 moles of water, right? The coefficient for AlOH3 is 2. Coefficient for water is 3. So my recipe says that 2 of these make 3 waters. But we're not talking about starting with 2 of these. We've got 6 of these, right? So we're going to have to scale this recipe up so that we have 6 of these, right? So I can take 6, divide by 2. That's 3, right? So this is the factor by which I have to multiply my recipe. So what I'm going to do is I'm going to take 3 and multiply that by the whole recipe. And that's going to give me a new recipe that's going to have the same proportions, but it's just going to be for a larger amount. All right, so then 3, when I multiply this out, I'm going to end up with 6 aluminum hydroxides, 3 aluminum oxides, and 9 waters. So then this equation has the same exact proportions as this one, right? The recipe still has everything in the same proportion. The only difference is that this has been scaled up for 6 moles of aluminum hydroxide instead of just for 2, right? And that's what the question's asking for. It's asking for 6 moles of aluminum hydroxide. How many moles of water? Well, looks like it's 9, right? It looks like it's 9 moles of water. Right? Now, this recipe way can make a lot of sense, right? But it's also a lot of work, right? I mean, I wrote a lot, right? I rewrote the whole equation. It's kind of a hassle if you had to do a whole bunch of other things too in the same problem, right? Like if it was just a mole to mole problem, this is perfect, right? If it's just a mole to mole problem, this is perfect. But if I was given grams of aluminum hydroxide instead, I wouldn't know, right? I wouldn't know what this factor has to be yet because I don't know what the moles are. So I would have to start using conversion factors. So that's why it's important to know how to use those conversion factors. Because if you're dealing with other units other than moles, it's kind of unavoidable, right? If your units are anything other than moles, then you have to convert from grams to moles first. And so it's not obvious how the recipe has to get scaled. In this case, it is. In this case, it is. So you can do it like this. But let's demonstrate. Let me demonstrate the conversion factor. We started off with 6 moles of aluminum hydroxide. 6 moles of aluminum hydroxide. You're going to multiply by a ratio of the coefficients. The coefficient of water, and we're looking at the original balanced equation now, not this modified one, but the original balanced equation. Coefficient for water is 3, and the coefficient for aluminum hydroxide is 2. So we're going to end up multiplying by 3 over 2, right? 3 over 2 times 6 is going to get me 9 moles of water. Same answer, right? Same answer. All right, let's look at another one. All right. So we're moving on to number 4 now on the quizzes. So you're going to have the same balanced equation. Same balanced equation. So let's see. 2 aluminum hydroxides decompose into aluminum oxide plus 3 waters, right? That's the balanced chemical equation. And now the question is, how many moles of aluminum hydroxide are needed to produce 15 moles of water? How many moles of AlOH3 are needed to produce 15 moles of water. So let's just do this one of a conversion factor. 15 moles of water is what we're starting with. We're going to multiply by a conversion factor, and we want to end up with moles of AlOH3. So we're going to take this coefficient and this coefficient and set up a ratio. We're going to set up a ratio. In this case, we're converting from water to aluminum hydroxide. So you want water on the bottom, aluminum hydroxide on the top. So it's going to be 2/3, right? You're converting from water to aluminum hydroxide. The number of aluminum hydroxides is less than the number of waters, right? This coefficient's smaller, right? 2 of these make 3 of these. Okay. So let's see, 15 times 2/3, that's going to be, let me draw it in black, that's going to be 10 moles of aluminum hydroxide, right? So that kind of makes sense. Remember, 2 aluminum hydroxides makes 3 waters. So if I scale this up to 15, that's like multiplying by 5, right? So I'm going to have to multiply this by 5 too. And so you're going to get 10. Right? 10, which is exactly what we got with the conversion factor. All right. Number 5. Same equation still. Same equation. But now the question is, how many moles of aluminum oxide must have been produced if 9 moles of water was produced? So how many moles of Al2O3 must have been produced if 9 moles of water were produced? Okay, so we're converting 9 moles of water, we're converting that to moles of Al2O3. And so if we think about this chemical equation as a recipe, then we can say that every time one Al2O3 is made, 3 waters are made, right? So that's the relationship, right? You make 3 waters every time you make one of these, right? 3 versus 1, 3 versus 1. But we're not making 3, right? We're making 9, right? So that's going to be more. We're going to have to scale this up, right? So if I set up the conversion factor, I have 9 moles of water. I'm going to multiply by, let's see, I want to convert 2 moles of Al2O3. So that's going to go on the top. Water is going to be on the bottom so that they cancel. And then the conversion factor is going to be 1/3. So 9 times 1/3 is going to be 3 moles of Al2O3. Which makes sense, right? Remember, 1 mole is made for every 3 moles. So if I make 9 moles of water, that's 3 times as much. Well, 3 times as much as 1 is 3. Perfect. All right, moving along. Number 6. All right, now we've got calcium sulfate plus lithium fluoride. That's exciting. So let's see. Oops, got a little too excited there. Calcium sulfate plus lithium fluoride. Right, so that's going to be a double replacement reaction. We're going to end up with calcium fluoride plus lithium sulfate. And then to balance it, I need a 2 here. Perfect. All right, so let's see what the question is. The question is, how many moles of lithium sulfate can be produced from 0.256 moles of lithium fluoride? All right, so let's see. How many moles of lithium sulfate can be produced from 0.256 moles of lithium fluoride? All right, so this is a recipe, right? We're gonna, if we look at the recipe, 1 calcium sulfate plus 2 lithium fluorides makes 1 calcium fluoride plus 1 lithium sulfate. So the relationship is that 1 lithium sulfate is made for every 2 lithium fluorides. But we're not starting off with 2. Instead, we're starting off with a much smaller number. We're starting off with 0.256. So we're going to have to scale this recipe down now. We're actually going to have to make this smaller, right? So let's see. We're starting off with 0.256 moles of LiF. We want to convert to moles Li2SO4. And let's see, we want lithium fluoride to cancel, so I'll put that in the bottom here because it's in the top here. That'll cancel. And then I need lithium sulfate on the top. And then the coefficients go here. The coefficient for lithium sulfate, that's 1. That's going to be here. And the coefficient for lithium fluoride, that's 2. That's going to be here, right? So 0.256 times 1/2, that's going to be my answer, right? 128. So let's ask ourselves, does it make sense? Well, 0.128 is half of 0.256. So we're making half as much lithium sulfate as we started off lithium fluoride with, right? Well, that's what my equation says. 2 of these makes 1 of these. So this number should always be half of this number, right? This has to be half of 0.256. Makes sense. All right. Number 7. Okay, same equation. Same equation. Calcium sulfate plus lithium fluoride makes calcium fluoride plus lithium sulfate, right? And then we need 2 of these. And the next question, question 7, how many moles of calcium sulfate are needed to produce 3.97 moles of calcium fluoride? So how many moles of calcium sulfate are needed to make 3.97 moles of calcium fluoride? So, all right, let's look at this. We've got 3.97 moles of calcium fluoride, and we're trying to convert this to moles of calcium sulfate. And we know, based on the equation, that 1 mole of calcium sulfate plus 2 moles of lithium fluoride makes 1 mole of calcium fluoride plus 1 mole of lithium sulfate. All right. So the relationship between these two things, well, 1 mole of calcium sulfate makes 1 mole calcium fluoride. So they're going to be equal numbers. So if I need to make 3.97 moles, I need 3.97 moles. Right? They're gonna be the same numbers. So my answer is going to be 3.97 moles of calcium sulfate. And I can prove it with the conversion factor. 3.97 moles calcium fluoride. You multiply by a ratio of the coefficients. So calcium fluoride on the bottom, calcium sulfate on the top. This is going to give me moles of calcium sulfate. Now, the coefficient for calcium sulfate is 1. So I'm going to put a 1 there. And the coefficient for calcium fluoride is also 1. So I take 3.97 and I multiply by 1. That gives me 3.97. All right. Let's see. Number 8. Number 8 is about octane, the combustion of octane. So let's look at that equation. So octane, C8H18, we're going to burn it. So that means we're reacting with oxygen. And that means we're going to make CO2 and water. Let's see, 8 carbons, 18 H's, so I need a 9 here. 8 times 2 is 16, plus 9 is 25, so I need a 25 over 2 here. But I don't want to have a fraction, so I'm going to multiply my entire equation by 2. And so I'm going to end up with 2, 25, 16, and 18. All right, now let's see, what was the question? Question was, how many moles of CO2 can be produced from 4.75 moles of octane? So how many moles of CO2 can be produced from 4.75 0.75 moles of octane. Right? So we're trying to make CO2 and we're making it from 4.75 moles of octane. We know that 2 moles of octane makes 16 moles, right? 2 moles of octane makes 16 moles, right? But we don't have 2. Instead, we've got 4.75, right? So we're going to have to scale this up, right? Now you can do it the recipe way. 4.75 divide by the coefficient of what you're starting with. Let's see, that's 2.375. And then you multiply the whole equation by that, right? So you would get, let me write it out. See, this is where it gets a little bit more tricky because you got like a weird number, right? Maybe you don't want to do this if you have a weird number like that. Maybe the conversion factor method is going to be easier in this case, perhaps. Let's see. All right, you're going to take the whole thing and multiply by 2.375. So that's going to give us 4.75 octanes plus, now 25 times 2.375. That's a big number. 59.375 oxygens. And then 16 times 2.375, that's 38 carbon dioxides. And finally, 42.75 waters. So the answer, how many moles of CO2 are made from 4.75 moles of octane? Well, looks like it's 38. Looks like it's 38 moles of CO2, right? All I did was I had a recipe. I had a recipe for making CO2 from 2 moles of octane, and that gave me 16. And instead of starting with 2, I started with 4.75, which means that I had to multiply my recipe by this factor. And that gives me 4.75 moles of octane, and that ended up leading me to 38 moles of CO2. Now, the conversion factor method in this case probably is a little bit quicker and a little bit easier. Let's look at it. 4.75 moles of octane. You're going to multiply by a conversion factor, which is a ratio of my coefficients in the original balanced equation, right? So that's going to be, let's see, we're converting to CO2. So that's going to be on the top. We're converting from octane. So that's got to be on the bottom. The coefficient for CO2 is 16. And the coefficient for octane is 2. So we're just going to do 4.75 times 16, then divide it by 2. And that's going to get us 38 moles of CO2. Same answer. All right? So let's see. Number 9 deals with the same equation. Number 9 deals with the same equation. So let's write that out again. 2 octanes plus 25 oxygens make 16 carbon dioxides plus 18 waters. And the question is, how many moles of O2 are needed to react with 2.235 moles of octane? How many moles of O2 are needed to react with 2.235 moles of octane. Okay, so let's set up a conversion factor. 2.235 moles of octane we're converting to moles of O2. So we need O2 on the top and octane on the bottom. And if you look at the coefficients in the equation, my coefficient for octane is 2. My coefficient for water is 25. I'm sorry, for oxygen is 25. So we're going to take 2.235 and multiply by 25 over 2. So that's going to be about 27. Actually, let me do that in black ink. .9 moles of O2. It's actually 27.9 for if you want to be slightly more precise. Okay. All right, moving along. We've got 2 more examples, both dealing with the combustion of octane. So let's get to it. All right, number 10. How many moles of CO2 must have been produced if 11.98 moles of water was produced? How many moles of CO2 must have been produced if, now what was the number again? So I've got a terrible short-term memory. 11.98 moles. Of water were produced. All right, so we're taking 11.98 moles of water, and we want to convert to moles of CO2. And we know that 18 moles of water are produced along with 16 moles of CO2. But we don't have 18. We've only got 11.98. But we want to maintain this 16 to 18 ratio, right? 16 to 18 is the ratio between CO2 and water. So we really just need to figure out what is 16 eighteenths, right? 16 over 18, what that fraction, what fraction of 11.98 is that, right? We know that there's less CO2 than water, so it's going to be less than 11.98. Let's look at it. 11.98 moles of water. You're going to multiply by the ratio of the coefficients. You want to end up with CO2, so that goes on top. You want to cancel water, so that goes on the bottom. You're dealing with 16 CO2s, so that goes here, and 18 waters, that goes there. And then 11.98 times 16 over 18. That's 10.65. moles of CO2. All right, last one. We've got octane. Plus 25. Right, same equation as the last couple examples. Number 11, how many moles of O2 are needed to produce 0.685 moles of water? How many moles of O2 are needed to produce, let's see, what was that number again? See, I can't remember the number. There's no way I can remember the number. 0.685. 0.685. Moles of water. All right, so we've got 0.685 moles of water, and we want to convert to moles of O2. So we know that 25 moles of O2 makes 18 moles of water, right? So we need more oxygen than the water, right? So we're going to need more than 0.685, but it's going to be a lot less than 25 because we're making a lot less than 18. We're only making 0.685. Let's see. 0.685 moles of water multiply by the conversion factor. So ratio, water on the bottom, O2 on the top, so that we end up with moles of O2. And that means that, you know, my coefficient for water is 18, so that goes on the bottom. My coefficient of O2 is 25, so that goes on the top. So we end up getting 0.685 times 25 over 18. So that's going to be 0.95 moles of O2. All right, so those were all the problems from the quizzes just a couple days ago. All right, so I hope this video was helpful. I hope you have a better understanding now of how to solve a mole-to-mole problem and how to use a balanced chemical equation to answer a variety of questions about the moles of one substance, you know, versus the moles of another. Okay? Have a great weekend.